Good afternoon. Today we're going to explore naive Bayes, not just as a classifier, but as a probabilistic philosophy within machine learning. When we look at this title slide, it may appear simple. Two words, naive Bayes, but those two words carry significant theoretical weight. Bayes refers to Bayesian probability, a framework for updating beliefs based on evidence. Naive refers to a simplifying assumption, one that dramatically reduces computational complexity but introduces structural bias. What makes this algorithm powerful is not complexity. It is disciplined probabilistic reasoning under structured assumptions. As we move through this presentation, I want you to focus on three themes. First, what assumptions does this model make? Second, when are those assumptions tolerable? And third, how do we evaluate whether simplicity is strategically appropriate? This will not be a coding session. This will be an examination of reasoning under uncertainty. And by the end, you should be able to evaluate naive Bayes not emotionally, not as simple or basic, but analytically. Let's begin. On this slide, we see a broader context diagram. Machine learning splits into two major categories, supervised learning and unsupervised learning. Within supervised learning, we see classification and regression. Naive Bayes lives here, under classification. That matters, because classification is fundamentally about assigning discrete labels based on observed data. Now, conceptually, what does naive Bayes do? It calculates the probability of a class given observed features, not the distance to a boundary, not the margin between hyperplanes, not an optimized weight vector. It calculates probability. Specifically, it uses prior knowledge, what we already believe about class distribution, and updates that belief after observing features. This is Bayesian reasoning. We start with a prior belief about the likelihood of each class. We observe data, we update that belief, we compute a posterior probability. Then we select the class with the highest posterior probability. Now here is where the naive assumption enters. The model assumes that the features are conditionally independent of each other given the class label. That is a strong assumption. In real data, age and salary often correlate. Text features co-occur, medical indicators interact. Yet the algorithm assumes independence. Why? Because modeling joint probability distributions directly becomes exponentially complex as feature count increases. The independence assumption transforms a high-dimensional joint probability into a product of individual probabilities. That simplification is what makes the model scalable. And despite being naive, it often performs extremely well, particularly in high-dimensional spaces like text classification. This is the paradox we will continue to examine. This slide is critical because this is where we stop thinking about performance and start thinking about structure. The first assumption listed is the most important. The features are conditionally independent of each other. Let's slow down here. Conditional independence means that once we know the class label, the features no longer influence one another. In other words, if we already know whether someone purchased, then age and estimated salary are treated as independent signals. In the real world, that is rarely perfectly true. Age may influence salary. Salary may correlate with purchasing power. Features often interact in subtle ways. So why make this assumption? Because without it, we would need to estimate the full joint probability distribution of all features simultaneously. And that becomes computationally explosive as the number of features increases. The independence assumption reduces that complexity from exponential growth to linear multiplication of individual probabilities. That is a massive simplification. Now, the second assumption listed is that each feature is equal in terms of weightage and importance. What does that mean conceptually? It means the model does not learn feature importance the way tree-based models do. There are no learned weights like in logistic regression. Each feature contributes probabilistically, but not hierarchically. The influence emerges from the distribution parameters, not from explicit weight optimization. The third assumption relates specifically to Gaussian naive Bayes. It assumes features follow a normal distribution. That means within each class, each continuous feature is modeled as a bell-shaped curve. If that assumption is violated severely, for example, if distributions are heavily skewed or multimodal, the probability estimates may degrade. Notice what we are seeing here. This model is built entirely on assumptions, and those assumptions define its boundaries. Understanding them is not optional. It is the difference between deploying the model intelligently and blindly. Now we move into evaluation. Let's begin with the advantages. The slide lists that it requires a small amount of training data. Why? Because it estimates relatively few parameters. It does not attempt to learn complex interactions. It simply estimates class priors and feature distributions within each class. Fewer parameters often mean less data required. Next, it handles continuous and discrete data. That flexibility comes from the different variants: Gaussian for continuous data, multinomial for counts, Bernoulli for binary features. It is also described as very simple, fast, and easy to implement, and that matters operationally. In production systems, training time and computational efficiency matter. Not every organization has unlimited compute resources. Finally, it supports both binary and multi-class classification problems. That scalability across class structures increases its utility. Now the disadvantages. The independence assumption is highlighted again. It is almost impossible to find real-world data where features are fully independent. So we must ask, how much violation is tolerable? That is a judgment call. The second limitation listed is the zero frequency problem. This occurs when a feature value appears in the test data, but was never observed in training for a particular class. If the model assigns a zero probability to that feature, the entire class probability collapses to zero. That is dangerous. This is why smoothing techniques are commonly applied. Conceptually, smoothing prevents absolute certainty about unobserved events. It acknowledges that absence in training does not imply impossibility. So again, we see the model is efficient, but it requires disciplined probability handling. Now let's talk about where this algorithm actually lives in the real world, because theory is useful, but application is where assumptions are tested. The slide lists several domains: real-time prediction, multi-class prediction, text classification, spam filtering, sentiment analysis, recommendation systems. But instead of reading those as categories, let's think structurally. What do these problems have in common? They involve many features, often thousands. In spam filtering, every word in a vocabulary becomes a potential signal. In sentiment analysis, word presence, frequency, or context becomes predictive. In recommendation systems, user behavior, clicks, views, and interactions become probabilistic indicators. Now imagine trying to model all interactions among those features. The combinatorial explosion would be enormous. Naïve Bayes does something radical. It refuses to model interaction structure. It says, I will treat each feature as contributing independently. And surprisingly, that is often enough. In real-time prediction environments, such as filtering emails or ranking content, speed matters. Inference must happen instantly. There is no time for complex iterative optimization at prediction time. Naïve Bayes computes probability directly. It multiplies class conditional likelihoods. It produces a result immediately. That efficiency is not an accident. It is the result of a simplifying assumption. And that is the theme you should notice across all these applications. The algorithm works best when dimensionality is high, interactions are weak or tolerable, and speed is critical. It is not flashy, it is not complex, but it is operationally reliable. And that reliability is why it continues to appear in production systems, even alongside far more sophisticated models. Now we transition. Up to this point, we have discussed theory, assumption, strengths, and application domains. This slide marks the shift from conceptual framing to structured implementation. But I want to be clear about something. When we say go over the code, we are not talking about memorizing syntax. We are examining the architecture of a machine learning pipeline. Because what matters at this level is not whether you can write a function call. What matters is whether you understand why each stage exists. Every serious modeling workflow follows a disciplined structure. We import tools, we load and inspect data, we validate assumptions, we prepare features, we split into training and testing sets, we train, we evaluate. That structure reflects scientific reasoning, not programming. Naïve Bayes is just one model inside that structure. And as we walk through the subsequent slides, notice something important. The workflow does not change because the model changes. Whether you use Naïve Bayes, logistic regression, or random forest, the discipline remains the same. That is what separates experimentation from engineering. So from here forward, as we examine each stage of the pipeline, think in terms of reasoning, not code. What problem is this step solving? What risk is it mitigating? What assumption is it validating? Because every stage exists for a reason. Now we see the imports. On the surface, this looks mechanical. Libraries for data handling, visualization, model selection, the Gaussian Naïve Bayes classifier, evaluation metrics, statistical testing. But conceptually, this slide tells us something deeper. Machine learning is interdisciplinary. It requires data manipulation tools, statistical analysis, visualization for insight, model construction, model evaluation. Notice that statistical testing is included. That matters. Because Gaussian Naïve Bayes assumes normally distributed features, and that assumption must be evaluated, not assumed. This slide reflects preparedness. We are assembling the instruments required to explore, validate, model, and evaluate. In research terms, this is a methodological setup, and methodology determines credibility. On this slide, we see the code responsible for loading the data set into the environment. Conceptually, this step represents the transition from abstract modeling to applied data analysis. Before any assumptions are evaluated, before any distributions are examined, before any model is trained, we must establish access to the data itself. Loading the dataset is not a trivial mechanical step. It defines the raw material upon which all probabilistic reasoning will be built. At this stage, nothing has been interpreted, nothing has been transformed, nothing has been validated. We are simply introducing the dataset into the analytical environment. This moment marks the beginning of empirical engagement. Every modeling decision that follows, from assumption checks to training, depends entirely on the integrity of this initial data ingestion step. And that is why even a simple loading operation matters within the broader modeling pipeline. Now we see the data itself. This is the first real look at the structure we are modeling. We observe several columns: user ID, gender, age, estimated salary, purchased. Immediately we can begin reasoning conceptually. User ID is clearly an identifier. It does not contain predictive signal in a meaningful statistical sense. It uniquely identifies an individual, but it does not describe behavior. Gender is categorical. Age and estimated salary are continuous numerical features. Purchased is the target variable, a binary outcome indicating whether the individual made a purchase. Now pause and think structurally. We are trying to predict a behavioral outcome, purchase decision, based on demographic and economic indicators. This is a classical supervised classification problem. The presence of continuous predictors suggests that Gaussian Naïve Bayes is an appropriate variant because it models each feature within each class using a normal distribution. Notice something else. The dataset is tabular, structured, clean. This is not high-dimensional text data. This is low-dimensional numeric data. That changes how we think about the independence assumption. With only two primary continuous predictors, age and salary, the independence assumption becomes more interpretable. We can directly examine whether age and salary are strongly correlated. If they are weakly correlated, the assumption becomes more defensible. If they are strongly correlated, the model's structural bias increases. But we cannot know that yet. At this stage, we are simply observing. Looking at actual rows also helps us internalize scale. Ages range across adulthood. Salaries span different income levels. Purchase decisions vary. This gives us intuition, and intuition matters before modeling, because models are abstractions built on data realities. If we do not understand the scale and nature of the data, we cannot responsibly interpret results later. So, slide 9 is not just a preview, it is the moment where abstraction becomes tangible. This is the foundation upon which the probabilistic model will operate. On this slide, we see the code used to inspect the dataset's structure. Conceptually, this represents the transition from loading raw data to validating its internal organization. At this stage, we are not modeling. We are verifying. Every serious machine learning workflow requires structural inspection before analysis. We need to understand how many records are present, what data types each column contains, whether there are inconsistencies, whether missing values exist. The presence of inspection code on this slide signals methodological discipline. We do not assume data quality, we test it. This step protects us from silent failures later in the modeling process. For example, if a categorical variable is misinterpreted as numeric, probability estimation becomes invalid. If missing values are present but unaccounted for, class conditional distributions become distorted. So even though this slide displays code, the underlying concept is validation. It is the checkpoint before exploration. Before we analyze distributions, before we test assumptions, before we train the model, we confirm structural integrity. That confirmation is foundational to probabilistic modeling. Now we move from structural inspection to statistical summarization. This slide shows the descriptive statistics of the dataset. We see measures such as count, mean, standard deviation, minimum and maximum values, quartiles. This is our first quantitative overview of the feature distributions. Conceptually, this step serves several purposes. First, it allows us to understand scale. What is the average age? What is the range of salaries? Are there extreme outliers? Second, it provides insight into variance. Variance matters for Gaussian Naïve Bayes because the model estimates class conditional distributions based on mean and variance. If variance is extremely large or extremely small, probability densities change accordingly. Third, descriptive statistics help us detect anomalies. If salary ranges were unrealistic, for example, negative values, we would immediately detect a data integrity issue. Now notice something important. This summary is aggregated across all classes. It does not yet separate purchased versus not purchased. So at this stage, we are understanding the global distribution of features. Later, we will examine class conditional distribution. But before comparing classes, we must understand that dataset as a whole. Descriptive statistics are not decorative. They provide the numerical intuition necessary to interpret model behavior later. Because when the model estimates probabilities, it does so using distribution parameters. And those parameters emerge directly from the data we are summarizing here. So this slide represents statistical grounding. Before we make probabilistic claims, we understand the raw numbers. That discipline prevents misinterpretation. Now we begin shaping the dataset for modeling. This slide shows the removal of columns that are not relevant for prediction, specifically user ID and gender, and the retention of age, estimated salary, and purchased. Conceptually, this is feature selection. User ID is an identifier. It uniquely distinguishes individuals, but it carries no behavioral meaning. Including it would introduce noise without signal. Gender is categorical. It may contain predictive value in some contexts, but in this implementation the focus is on continuous predictors that align with the Gaussian naive Bayes assumption. So we narrowed the dataset. We retain age, a continuous demographic variable, estimated salary, a continuous economic variable, purchased, the binary target variable. This narrowing is intentional. Machine learning is not about throwing every available variable into a model. It's about selecting variables that align with the modeling assumptions and the research objective. Now think probabilistically. Gaussian naive Bayes models each feature within each class as normally distributed. By retaining continuous numerical variables, we ensure compatibility with that assumption. Feature selection is not cosmetic. It directly influences the quality of probability estimation. Including irrelevant variables can distort distributions and weaken predictive performance. Excluding structurally incompatible variables can improve alignment between data and model. This slide represents the moment where raw data becomes modeling data, and that transformation must be intentional. Now we arrive at one of the most important stages in the entire modeling pipeline: exploratory data analysis. This is where we stop assuming and start validating. The slide includes distribution visualizations, box plots, a correlation matrix, and the Shapiro-Wilk test. Each of these serves a specific conceptual purpose. Let's begin with distribution plots. Gaussian naive Bayes assumes that continuous features follow a normal distribution within each class. So we must ask, do age and estimated salary resemble bell-shaped distributions? If the distributions are severely skewed or multimodal, the Gaussian assumption becomes questionable. The histograms allow us to visually inspect this alignment. Next, the box plots. Box plots allow us to compare feature distributions across classes, purchased versus not purchased. If there is meaningful separation between the medians or interquartile ranges of the classes, that suggests predictive signal. If both classes overlap almost entirely, classification becomes difficult regardless of model choice. Now consider the correlation matrix. The independence assumption states that features should be conditionally independent given the class. If age and estimated salary are highly correlated with each other, the independence assumption weakens. Strong inter-feature correlation increases the likelihood that the model's simplifying assumption will distort probability estimates. Low correlation strengthens the defensibility of the model. Finally, the Shapiro-Wilk test. This statistical test evaluates whether the feature distribution deviates significantly from normality. If the p-value indicates non-normality, we must consider whether the deviation is severe enough to undermine the Gaussian assumption. Now, notice the discipline here. We are not blindly fitting a model. We are interrogating assumptions before training. This is what separates applied machine learning from superficial implementation. Assumption validation is not optional in probabilistic models. It is foundational. This slide represents methodological rigor. We examine distribution shape, we examine class separation, we examine correlation structure, we evaluate statistical normality. Only after these checks do we proceed, because probability-based models are only as reliable as the assumptions they stand on. Now we see the visual results of the exploratory analysis. This slide contains histograms and box plots that allow us to examine the behavior of age and estimated salary in relation to the purchased variable. Let's begin with the histograms. When we look at the distributions, we are asking a very specific question. Do these features resemble a normal distribution? Gaussian naive Bayes assumes that within each class, each feature follows a bell-shaped distribution characterized by a mean and a variance. If the histogram appears approximately symmetric and unimodal, that supports the assumption. If it appears heavily skewed or irregular, that weakens it. The goal is not perfection. The goal is reasonable approximation. Most real-world data is not perfectly normal, but if it approximates normality closely enough, Gaussian naive Bayes remains effective. Now, look at the box plots. The box plots separate the feature distributions by class, purchased versus not purchased. This visualization allows us to assess class separation. For age, we observe that individuals who purchased tend to cluster in a different range compared to those who did not. There is overlap, but there is also a noticeable shift. For estimated salary, we observe a similar pattern. Higher salary ranges appear more associated with purchasing behavior. These visual separations matter because naive Bayes does not create complex nonlinear boundaries. It relies on differences in class conditional distributions. If those distributions differ meaningfully, the model can distinguish classes probabilistically. If they are nearly identical, the model has little signal to leverage. So this slide tells us something encouraging. There appears to be distributional difference between classes. There appears to be approximate normal structure. That combination supports the use of Gaussian naive Bayes. Visual evidence strengthens the conceptual justification, and that justification is what gives confidence before training. Now we examine the correlation matrix. This is one of the most important visual diagnostics for naive Bayes. Remember the independence assumption. The model assumes that features are conditionally independent given the class. While perfect independence is unrealistic, low correlation between features strengthens the validity of the assumption. So let's interpret what we see. Age and estimated salary show relatively low correlation with one another. That is encouraging. If those two predictors were strongly correlated, the independence assumption would be strained. Strong correlation would mean that the information contained in one feature overlaps significantly with the other. Naive Bayes would treat them as independent contributions, potentially double counting the same signal. But here, the correlation between age and salary appears modest. That reduces structural distortion. Now, look at the correlation between each feature in the target variable, purchase. Both age and salary show positive association with purchasing behavior. That means as age increases, the likelihood of purchase increases. Similarly, higher estimated salary is associated with higher purchasing probability. These associations suggest predictive signal, and predictive signal is necessary for classification. The heat map visually reinforces the quantitative relationships. Darker or more intense colors indicate stronger relationships. But notice something subtle. Even though age and salary correlate with purchase, they are not perfectly correlated. There is variance within classes. That variance is what naive Bayes models using Gaussian distributions. If there were no variance, classification would be trivial. If there were no correlation, classification would be impossible. We are looking for balance, moderate association with the target, limited association between predictors. That balance supports the model structure. This slide gives us structural reassurance. The independence assumption is not grossly violated, and the predictors carry meaningful information. That combination justifies proceeding. Now we arrive at a foundational principle in machine learning: separation between training data and testing data. This slide shows the step where the dataset is divided into two subsets. One subset will be used to train the model. The other will be used to evaluate it. Conceptually, this protects us from self-deception. If we train and evaluate on the same data, performance metrics become inflated. The model memorizes patterns specific to that dataset. But memorization is not generalization. By separating the data, we simulate future observations. The test set represents unseen data, the real-world scenario, where the model must make predictions on new inputs. Now notice the use of stratification. Stratification preserves the proportion of the target classes in both the training and testing sets. Why does this matter? If the class distribution shifts between training and testing subsets, performance metrics can become misleading. For example, if the training set contains mostly non-purchasers and the test set contains mostly purchasers, evaluation becomes unstable. Stratification ensures class balance consistency. Now, think probabilistically. Naïve Bayes estimates class priors from the training data. If class proportions are distorted during splitting, prior probabilities become unreliable. So stratification supports stable prior estimation. This slide represents methodological integrity. It ensures that evaluation is honest. It ensures that prior probabilities are consistent. And it ensures that performance metrics reflect generalization rather than memorization. Without proper splitting, model evaluation becomes meaningless. Now we introduce feature scaling. At first glance, scaling may seem routine, almost mechanical, but conceptually, it plays a stabilizing role in probabilistic modeling. The slide shows standardization being applied to the training data, and then the same transformation applied to the test data. Standardization centers the data around zero and rescales it to unit variance. Now let's think about why this matters in the context of Gaussian Naïve Bayes. The model estimates a mean and variance for each feature within each class. If one feature operates on a vastly larger numeric scale than another, for example, salary measured in tens of thousands versus age measured in years, the magnitude difference can affect numerical stability during probability density computation. Scaling ensures comparability in magnitude. It does not change relationships. It does not distort ordering. It simply normalizes scale. There is also a methodological discipline here. Notice that the scalar is fit only on the training data, then applied to the test data. This prevents data leakage. If we use the entire data set to compute scaling parameters, information from the test set would leak into the training process. That would contaminate evaluation. So scaling is not only about numerical stability, it is about preserving experimental integrity. Even though Gaussian Naïve Bayes can operate without scaling in many contexts, applying standardization ensures consistent behavior and stable estimation. This slide reflects careful pre-processing, ensuring that the model operates on normalized inputs while maintaining strict separation between training and testing data. Now we reach the core modeling step. This slide shows the creation of the Gaussian Naïve Bayes classifier and the fitting of that model to the training data. Conceptually, what happens during training? Unlike many other machine learning algorithms, Gaussian Naïve Bayes does not perform iterative optimization. There is no gradient descent. There is no boundary search. There is no tree construction. Training consists of estimating parameters, specifically for each class, purchased and not purchased, the model estimates, the prior probability of the class, the mean of each feature within that class, the variance of each feature within that class. That's it. These parameters define a Gaussian distribution for each feature conditioned on the class label. So when the model is fit, it is essentially learning the shape of the probability distributions that describe age and estimated salary within each class. Later, when a new observation arrives, the model computes the likelihood of that observation under each class distribution. It multiplies those likelihoods because of the independence assumption. It incorporates the prior probability, and it selects the class with the highest posterior probability. Training is therefore parameter estimation, not optimization. And that distinction matters because it explains why Naïve Bayes trains extremely quickly. It is not searching for a global minimum. It is computing statistical summaries. This slide marks the moment where assumptions become instantiated into a working probabilistic model. Everything prior prepared us for this step. Everything after will evaluate it. Now we move from training to performance. This slide represents the moment where the model is tested against unseen data. The classifier, trained on a training subset, is now used to generate predictions on the test set. Conceptually, this is where generalization is measured. A model is only useful if it performs well on data it has never seen before. So when predictions are generated for the test set, we are evaluating whether the learned probability distribution generalized beyond the training data. Now we examine evaluation metrics. The first metric is accuracy. Accuracy measures the proportion of correctly classified instances. It is intuitive, it is simple, but it can be misleading in imbalanced data sets. So accuracy alone is not sufficient. That is why the confusion matrix is also calculated. The confusion matrix provides a structured breakdown of predictions: true positives, true negatives, false positives, false negatives. Each of these components tells a different story. A false positive means predicting a purchase when none occurred. A false negative means failing to predict a purchase when one actually occurred. Depending on the application, these errors carry different costs. That is why we also examine the classification report. The classification report provides precision, how reliable positive predictions are. Recall how many actual positives are captured. F1 score, the harmonic balance between precision and recall. These metrics move us beyond raw correctness. They measure quality of classification under different perspectives. Now conceptually, notice something important. Naïve Bayes does not optimize directly for accuracy, it models probability. Evaluation metrics are external measurements applied after training. This distinction reinforces the idea that modeling and evaluation are separate processes. The model estimates distributions. The evaluation framework judges performance, and both are necessary. This slide represents accountability. It forces the model to justify its assumptions through measurable outcomes. Now we examine the actual performance outcomes. This slide presents the numerical results of the model's evaluation on the test set. We see an accuracy of approximately 87.5%. Let's interpret that carefully. An accuracy of 87% means that nearly 9 out of 10 predictions were correct on unseen data. That is strong performance for a model built on simplifying assumptions. But accuracy alone is not enough. The classification report breaks performance down by class. We observe precision and recall for both purchased and not purchased categories. If precision is high for the purchase class, that means when the model predicts a purchase, it is usually correct. If recall is high, That means the model captures most of the actual purchasers. Balanced precision and recall indicate that the model is not favoring one class disproportionately. Now consider the F1 score. The F1 score balances precision and recall. If both are strong, the F1 score will be strong. This suggests that the model is not only accurate overall, but consistent across error types. Now reflect conceptually. This performance was achieved without modeling feature interactions, without complex nonlinear transformations, without deep architectures. The model relied on class priors and Gaussian feature distributions. That simplicity produced robust results. This reinforces a critical principle in machine learning. Appropriate alignment between data structure and model assumptions can outperform unnecessary complexity. The results validate the earlier assumption checks. The distributions were reasonably normal. The correlation between features was modest. Class separation was visible. Those structural observations translated into measurable, predictive performance. This slide closes the loop between theory and empirical validation. Now we move from numbers to visual interpretation. This slide presents the confusion matrix as a heat map. The confusion matrix is not merely a table. It is a structural map of decision behavior. On one axis, we have the actual class labels. On the other axis, we have the predicted class labels. The diagonal entries represent correct classifications, true negatives, true positives. The off-diagonal entries represent errors, false positives, false negatives. Now look at the heat map. The diagonal cells are darker, indicating higher counts. That tells us the model correctly classified the majority of cases. The off-diagonal cells are lighter, indicating fewer misclassifications. This visual reinforcement confirms what the numerical metrics suggested earlier, but the visualization adds something important. It allows us to immediately detect imbalance. If one diagonal cell were much darker than the other, we might suspect class bias. If one off-diagonal cell were disproportionately large, we might identify systematic error in one direction. Visual inspection complements numerical reporting because numbers can sometimes hide asymmetry. Visualization exposes structure. Conceptually, this slide represents interpretability. Naive Bayes produces predictions based on probabilistic reasoning. The confusion matrix shows how those probabilistic decisions translate into real classification outcomes. It tells us where the model is strong. It tells us where it struggles. And it does so in a way that is immediately accessible. This is not cosmetic. It is analytical transparency. We have reached the conclusion of this modeling journey. But what matters here is not that we trained a classifier. What matters is how we approached it. We began with theory. We examined the foundational idea of Bayesian reasoning. We analyzed the independence assumption, not as a slogan, but as a structural simplification. We examined strengths and limitations honestly. We validated assumptions using exploratory data analysis. We inspected distributions. We evaluated correlation structure. We checked normality. We split the data properly. We scaled responsibly. We trained using parameter estimation rather than optimization. We evaluated performance using multiple metrics. And we visualized classification outcomes for interpretability. What this presentation demonstrates is something larger than naive Bayes. It demonstrates disciplined machine learning methodology. Naive Bayes is often described as simple, but simplicity does not mean superficial. It means controlled assumptions. And when assumptions align with data structure, simplicity can produce strong, reliable performance. The broader lesson is this: modeling is not about complexity. It is about alignment. Alignment between assumptions and data. Alignment between methodology and evaluation. Alignment between interpretation and decision making. Naive Bayes reminds us that strong probabilistic reasoning, when applied carefully, can be both efficient and effective. And that is a principle that extends far beyond this specific algorithm. Thank you.